Hi, I'm Romano, and this is my Physics 2211 lab one on constant velocity. And in this lab, I modeled constant velocity motion and compared what a computational model predicts to what we measured from video tracking. So over this presentation, I'll introduce the physics idea, the equations, and explain the experiment and how I got the initial conditions from Tracker, and then I'll show the results and what they actually mean. So the main idea is that if the net force is zero, an object keeps moving at the same speed in the same direction, which is Newton's first law, and then Newton's second law connects the force to motion. If there's a net force, there's acceleration. So for constant velocity, acceleration should be zero, meaning the net force should be approximately zero as well. Because of that, we expect the position versus time graph to be a straight line, and the slope of that line represents the velocity. So the goal of this lab is to observe that motion and compare a theoretical constant velocity model to a real measured motion. So the equations the model uses is here. The main idea is that the code updates the position in small time steps, and we use a velocity update and position update repeatedly over time. And if we assume the net force is zero, then acceleration is zero, so velocity should stay constant, and position should increase linearly with time. So the important takeaway is the model should produce a straight line position versus time graph if constant velocity is happening. So this is the glow script prediction for constant velocity. Since I set f net equal to zero, the model keeps velocity constant. So it is a straight line, and I will compare it later to the tracker data. So for the experiment, the object used was an expo marker, and the system is the marker itself. The surroundings include friction from the table, air resistance, gravity, and the normal force from the surface. Even if the marker moves to close to constant speed, those forces still can exist, and the key is whether they balance to make the net force near zero. And for the data pipeline, Tracker gives the measured position, GlowScript gives the predicted position, and then graphing everything in sheets to compare the two. So first, I recorded the expo marker moving in a straight line at a rough constant speed next to a meter stick, and then I imported the video into Tracker and calibrated the scale using the ruler so positions would be in meters. And then I tracked the marker frame by frame and exported time and position data. After that, I used Tracker data to set the initial conditions and entered those into GlowScript with a net force equal to zero. And then I graphed the outputs later and compared the measured versus predicted motions. So to make the model realistic, I needed the initial condition from Tracker, as I said. So the initial position comes from the start of the motion. Then for initial velocity, I estimated it from the data using change in position over change in time, basically taking the slope at the beginning. So the slide is showing where those starting values come from and how they're going to tie directly to the tracker data. And in here is where you can see the glow script. I plugged in the same starting information where we have the mass of the marker, the initial conditions, the delta t is equal to the frames per second. We have the total time is the while loop it is in, the net force is set equal to zero while using the position update formula. So this is where we actually compare them. The tracker data is an observed pattern and glow script is in the predicted position. Overall, the two forces follow the same trend and stay close, which supports the idea that the marker was moving at approximately constant velocity over the interval we analyzed, and the line of best fit also shows a very strong linear relationship as r squared is pretty close to 1, and that is exactly what we expect if the velocity is constant. So a few things that could have gone wrong throughout the lab is the tracking point inconsistency. I might have not clicked the exact same point on the marker in every frame, which could slightly shift the position. There could be a divot or imperfection in the surface, like a small bump or patch could change the friction for a moment, causing a small speed change, or the calibration scale error. The meter stick might not have been perfectly aligned with the marker's path, and that could create a small distance and scaling error. And so the what ifs and what does this mean? So if the axes were flipped, since I defined the motion as positive x, the slope is positive. If I define the motion in a negative direction instead, the graph will slope downward and positions would be negative, but the magnitude of the motion would stay the same, only the sign would change. And if the net force is about zero, what does that actually mean? And it doesn't mean that there are no forces, which is very key to know. It means that they cancel. So vertically, the normal forces cancel gravity. Horizontally, friction and air resistance can exist, but if the marker speed stays nearly constant, then the net force is still zero. So for this conclusion, Newton's second law is supported because the glow script predicts a linear position time graph for constant velocity, and when comparing it to the tracker data, the trends match closely and supports constant velocity and therefore net force approximately zero during the interval analyzed.